In this series, we're going to talk about multivariable functions. Actually, the real world is really based in looking at multivariable functions. In our algebra classes, we are really reducing the complexity of phenomena in the real world by only studying the relationship between one output variable and one input variable. A multivariable function is one that has one output but that has multiple inputs. So that's where multivariable comes from. So when you think of something like y equals 2x plus 3, that is actually called univariate. And it's called univariate because the uni part, implying 1, is actually related to the number of inputs. That's why we call it a univariate instead of a multivariate function. Multivariable function. So multivariable functions have multiple outputs. And as you can imagine, most things in the real world are that way. For example, when you go and rent a moving truck, you are actually, like U-Haul, for example, is going to charge you a daily rate, and they're going to charge you per mile. So if you only rent for one day, of course, you can you pay a constant $19.99 for that one day, but then 47 cents for each mile that you drive. So let's actually build this function the way it might look. And so since we know that we're going to be representing cost, we're going to model that based on the number of days and the number of miles that you drive it for. So let's define some variables. C equals your total cost, and we'll provide units. That's very important. And so now we'll say that D is the number of days of rental. And then I guess we could use M for miles driven. So M is the number of miles driven. And that's not daily, that's the total number of miles. So your total cost, well, it's $19.99 per day times the number of days that you rent the truck for, plus 47 cents times the number of miles that you drive. And to express this in function notation, just like we have done in the past, like here we might actually write f of x equals 2x plus 3. We'll do a similar thing here, except we'll say c of the two variables that we have, d and m. Now, it's not critical what order these go in. I mean, it's convenient to write them in the order that they appear in if variables appear independently in each term, but we just have to be clear on if we replace these with numbers, what the first and second numbers represent. And so this is going to be 1999d plus 0.47m. So we can begin to answer questions about this. Like, for example, what is the total cost when you rent the truck for 3 days and you drive 100 miles? And that would be, well, $19.99 a day for 3 days plus 47 cents a mile times the 100 miles that we drove. And so we could do the math on that, and we get, approximately, I'm going to guess here, that's about $60 or $59.97, and then this is going to be $47. So 60 plus 47 is going to be about $107 to do that. Okay, so there's one example of a multivariable function. So yeah, typically we'll reduce the total cost down to just looking at one day. But the function actually works this way. This is what they type into their computer, how many days you had it for, how many miles you drove, and they get your total cost. The future value of a $1 investment at rate of R compounded n times per year with P dollars of initial investment. We're really familiar with this. This is the compound interest formula. And the compound interest formula is a multivariable function. Now, so far we've only been treating this as a function of time, that P, R, and N were all given to us, but this is not necessarily true. So how could we write this function? Well, we could think about this as a multivariable function with inputs P, R, N, and T. And again, it doesn't really matter how you write it in function notation, as long as you do let somebody know what variables are in what position within the parameters. We call this the parameter set, and that could be written as P times 1 plus R over N to the NT power. And that has 4 input variables in reality, and the output is the future value. So let's actually look at one of these interpretations. Find a of 100, 0.05, 12, 15. So don't ever assume that, oh, this is the present value and this must be the rate. We do have to make sure that it's consistent with the notation we've chosen. And I've chosen here to use the notation A of P, R, N, T in that particular order. So that's what I mean by this is what's important, because if somebody actually wrote their function and the first parameter they had in their parentheses was t, this could actually mean 100 years for investment for $15. So as long as we know what each of these represents, so a of 100, 0.05, 12, and 15 would be $100 invested at 5% interest compounded monthly to the 12 times 15 years power. And if we do that math, we get $211.37 as the total amount of that future value. Okay, so what's our interpretation here? Well, you're going to make our $211.37 is the balance of a $100 investment at 5% compounded monthly for 15 years. Great. So we, based on knowing what those four constants are, we can come up with a numerical output. But that's not often what we want to do. Oftentimes what we want to do is study the relationship between the output variable and one of the input variables. So questions we might want to ask are, how big of an effect does n have on the future value? So maybe I want to write an equation that has f as a function of n. Or maybe the function of t, which is what we've been familiar with, looking at this idea that a t affects the future value. How big of an effect does r have on the future value? So if you increase the interest rate by 1%, what will that do? How big of an effect does p have on the future value? What will one more dollar do to your investment? So their multivariable functions are really hard to study if you're really going to let all these things vary at one time. It's kind of like if I were to build a garden and I started to do multiple things to that garden. So for example, I decided that this year last year my tomato crop wasn't good. So this year these are my tomato plants, and this is my little garden here. And so what I do is to see if I could better my yield or improve my yield, what I start to do is add a fertilizer. I also start to water more. I also start to, amend the soil, which basically means adding other nutrients to the soil, and I give it more sun. And suddenly what I find is that at the end of the season, I have these, big, beautiful tomato plants with lots of tomatoes, and they're delicious and everything is good. And I say, it must have been the fertilizer. That must have been what caused it. Well, wait a minute. Your improved yield, now that your yield is a function now of all of these variables, because you suddenly changed a bunch of factors. So you don't really understand, and nobody would, which one of these factors caused it. Maybe they all did, and maybe actually one of them improved it, but the other ones actually made it so that you could have even had a bigger yield, but because you maybe overwatered, that actually made your yield still much bigger than the previous year, but relatively speaking to how much you could have had, a little bit less. So it's kind of complicated. We don't want to, we can't think this way with experiments in particular. You can't make a bunch of changes and try to understand which one caused the relationship you were seeing. So in the moving truck example, one thing that we might want to do is, this was the cost as a function of days and miles, was 1999 D plus 0.47 M. So what we do is we can reduce the function. I just call it function reduction. This isn't something you could probably go Google, but we're going to reduce this function to what we're used to in algebra. Make this a bivariate relationship, meaning I just want to look at one variable and see how it affects the cost. So maybe what I could do is actually say, you know what, I want to look at the cost based on days, and what I'm going to do is I'm going to fix one of the variables. So this is going to be under the condition that I know in total, I've done the math, I'm going to end up driving a total of 100 miles, but I'm worried that this might take me multiple days because I'm busy, and but I don't want to, I'm not going to be able to just find one day in which to do it. So what I know is that my mileage is fixed at 100. Now what does that do? Well, mathematically, that just says that D is still a variable. I don't know what that's going to take on. I want to look at how cost will be affected as D varies. And now I'm going to fix the number of miles to 100. And if you do the math on this, really a lot of times what we'll do is we'll just say, okay, this is C of D. Now, it's kind of tricky to do. You have to keep remembering that this function is only applicable to the fact that you drive 100 miles. If you drive any more miles, you have to change the value of m. Okay, so the reason I do this is because this actually has taken a multivariable relationship and reduced it down to a univariate relationship. So now I can start to look at what effect does d have on the total cost. And as you notice, this is a linear function of the form mx plus b. Well, I can graph this now. So this is the total cost of the rental truck versus the number of days of the rental. And this is actually one thing that I missed up here that I really should have put is the fact that this is m equals 100. So that's very important to say that. You can't just show somebody this graph unless you tell them this is only your cost. You know, your cost will be $66.99 if you rent it for 1 day, assuming you drive 100 miles. Your cost is $86.98, assuming for 2 days, assuming you drive 100 miles, and so on and so forth. So each value of m will actually have its own corresponding graph of cost versus days. We can do the same thing with this function. Now, again, we want to reduce it to a bivariate relationship. So here we want to just build the function, do the function reduction, and then actually talk about what the function reduction has done and what it means. Okay, so what this means is that my present value is 100. Remember, this is P, R, N, and T, the way we had it listed. And so what I'm going to do is I'm going to fix all these other values. I'm going to fix the rate to 5%, fix the time to 15 years, fix the initial investment to $100, and see what would happen if I started to compound more and more. Okay, so this would mean that A of N, under the assumption that P is 100, R is 0.05, and T is 15, would reduce to the following. It would be 100 times 1 plus r over n, which is 0.05 divided by n. Now n is allowed to vary, meaning I'm gonna keep a variable in that place, to the n times t power. Well, t is fixed at 15 years. So now I want to see, okay, well, what is this going to look like mathematically? Okay, so if I begin to graph this function now the function that I'm graphing here is the function that we had on the previous slide with n as a variable. So now what I have is the future value as a function of the number of yearly compoundings. That's key here. So the future value, A, is varying as we change the number of annual compoundings. Now, it's kind of cool to look at this graph because if you compound once a year and then you go to compounding 2 times a year, your future value grows from $207 to $209. But you notice that as you start to vary from 3 compoundings a year to 4 compoundings a year, the difference is pennies on the dollar. And then furthermore, over here, when you vary from 16 to 17 annual compoundings, your balance really only changes by what is it, 46 cents, about a penny. And so as a result, we're seeing this graph kind of flatten out over here. We have this big change here from 1 to 2. Still a decent change from 1 to 2 to 3, and then as you can see, as this function, as the number of compoundings grows, there's less and less change in the future value. Now, again, this is only under the assumption of $100 invested at 5% for 15 years. So does this explain, does this say that, n doesn't matter? Well, no, it doesn't. Now, probably for every different constant that we picked in here, the relationship would probably be very much the same. In fact, it would be the same function. If I back up here a second, it would look the same way. It would still be this function here. It's just these constants can vary from example to example. So in the long run, the behavior will still kind of be this rational function, but it will be a little bit different. So the key point to understand here, or the key thing we should get out of this video, is that what we really want to do is we want to try to understand how the output changes with respect to one variable at a time while holding everything else constant. So we've done it quite literally. We've actually plugged in numbers for all of the other variables and made those things constant. That is, we treat the other variables as though they are unchanging. Now, do they change in reality? Of course they do, but we just want to understand how one thing varies with respect to another. So in the next videos, we'll start to analyze, well, how do we begin thinking about this in a more formal way without having to plug in numbers every single time?